All right, good. So, hello everyone. My name is Emil. I'm from the Charles University in Prague in Czech Republic. I'm going to be talking about a two-dimensional turbulence using superfluid helium. So there should be probably quasi-two-dimensional in superfluid turbulence, but it will be too long. And all of the work that I'm going to show is, of course, due to the postdoc research activity, and mainly these two students, Filip Novotný, Marek Talížen, are undergrads. So, my outline is that first I'll talk about whether two-dimensional turbulence in helium is possible at all, since the small scale is in helium very small. Next, how do we actually experimentally realize them with periodically driven flows? And then look at what I actually promised in the title, multi-stability and critical points. Good. So, someone should mention the turbulence cascade and how it looks like in 3D and 2D, so it's going to be me. So in 3D, as we all know, if we inject energy at large scales, we create eddies, vortices, and in homogeneous isotropic case, the energy is transferred to smaller and smaller scales until it's dissipated by viscosity. This happens because of something called vortex stretching, where when we write the Navier-Stokes equation in vorticity form, we get a term like this, which happens to do, what it does, it stretches and blobs of vorticity in converging flows, thus transferring energy into smaller scales. Now, of course, from the way this term looks like, it is not allowed in two-dimensional case, where velocity would be in a plane and vorticity would be perpendicular to it, and as a result, in two dimensions, in homogeneous isotropic case, the energy is not transferred to smaller and smaller scales, but rather is transferred up into larger scales, as can be seen on this simulation from this review that I stole, where the energy injection is localized at small wave numbers and cascades up. It's a classical case. Now, in helium, we get two liquids in one. We get a normal superfluid equation, normal and superfluid component, which intermixed below the superfluid transition point about 2.17 Kelvin, where we get something like an Euler equation for the superfluid and something like a Navier-Stokes equation for the normal fluid with the addition of these thermal terms. But this is of course not the whole story. The superfluid component, the circulation is quantized, as Luke already mentioned, and the quantization of circulation leads to the existence of quantized vortices, and these quantized vortices are responsible for dissipation. And and the equation of motion of a vortex looks like this. Luke already talked about it extensively and already told us why this is wrong the way I've written it because of improper treatment of the normal fluid. But if we ignore that for the moment, the two-fluid nature of the superfluid helium allows us first existence of multiple types of sound, the first sound, second sound, a fourth sound, where the normal fluid is stationary and the superfluid oscillates, and also allows construction of various DC flows. For our experiment, we will be using specifically this fourth sound, where by confinement, by geometrical confinement, we'll prevent the normal fluid from moving, and we'll only oscillate the superfluid component. Now, if we write down the equation of motion for the flow in the fourth sound, it's kind of interesting looking because it has the usual terms that we're used to, and the mutual friction basically reduces to this, where there are some material parameters. LVS, L is the number of vortices per unit area, and VS is the superfluid velocity, and this other non-dissipative term of the mutual friction, where there is superfluid vorticity, which is similar to L but oriented, and F is forcing. This, on the first glance, might look like what you would typically start with rotating two-dimensional turbulence. There's some large-scale linear dissipation and Coriolis force, but of course, there is a very important difference, is that the L is a complicated function of Vs, and omega S is not a system rotation, but a local vorticity. And as they are derived from experiments, from large-scale experiments, these alpha and alpha prime parameters look like this as a function of temperature. So by just changing the temperature, we can really change strongly the large scale linear dissipation. Now, how do we actually use the fourth sound? We study these flows in a nanofluidic Helmholtz resonators that look like this. This is about 1 centimeter by centimeter in size. Internally, a blown up picture looks like this, where we have a nanofluidic cavity, sandwich between two glass chips. And internally, we place two aluminum electrodes, and when there is flow in and out of the device, we see oscillating capacitance, and we measure the oscillating capacitance. The flow that exists in this device is an example of Helmholtz resonance. That's a Helmholtz resonance if you forgot from your undergrad physics. And we indeed get a FEM simulation, a flow that looks like this. This is the color scale, and the arrows indicate the magnitude of the flow velocity. Well, the frequency is given by the superfluid density mostly. Yeah, and we measure the velocity amplitude by just wiring it in a capacitance bridge, and measuring the oscillations of the capacitance. So when we have a system like this and we drive it strong enough, we drive the velocity amplitude high enough, the response, the resonant response of the device becomes nonlinear, and it becomes nonlinear in such a way that there is these Lorentzian shapes are kind of squished on top, that there is more dissipation that you would expect from the linear case. And this dissipation is due to vortices. How can we show this? Well, we redo the experiment from 1950s that Luca was talking about, that Joe Winan and Henry Hall did, where they used a second sound resonator, which they placed in a rotating system. We use a fourth sound resonator placed in a rotating system. Here you can see, I don't know why it's green, but you can see a cryostat with all the instruments rotating around this axis. The paper for this is here. And as we measure, the change in response is minuscule but resolvable. We go to up to 180 degrees per second with this iteration of the experiment, and we see can derive a formula that relates non-attenuated and attenuated amplitude and the mutual friction parameter, and you get a very good agreement with the number of vortices that you would expect simply from rotation. So now we see dumping, which is most likely and predominantly due to vortices that somehow appear in the flow. But are these vortices 2D? So again, this is going to be a vortex filament simulation, exactly the same kind that Luca was talking about, but a very simplified, much more wrong one, where we don't treat the normal fluid at all, where we treat it as completely stationary. And this is a basic example of what the vortices do. So if we have a colliding pair of vortices pinned between two planar walls, subject to a superflow velocity of 25 centimeters per second, and it's stationed in normal fluid, and we assume the normal fluid is stationary because this is only half a micrometer. So in our oscillating flow, the viscous penetration depth would be much larger than half a micrometer. So it wouldn't have much chance to oscillate. Now, when these vortices collide, they just annihilate very quickly within a few microseconds, and they don't really have a time to develop any complicated structure. Now, if I show it in a more realistic aspect ratios, you see that these vortices really don't develop any three-dimensional structure at all until they annihilate. This is still not a realistic aspect ratio of the experiment. The aspect ratios of the experiment are going to show is about 2,000, so half a micron tall, 1 millimeter wide. Now, even if we go to much larger confinement that we actually use, 10 micrometers, so that the vortices have much more freedom to move, and again, subject them to fairly high velocities, what we still observe What we still see is that there's some deformations on the vortices develops, but they still kind of retain the two-dimensional nature. They retain their definite circulation. They're going either up or down. That's what the blue and red colors mean. The blue have a negative circulation, and the red have positive circulation. And if we go to fairly ridiculously high velocities, now we observe a little bit more green ones. Those are like half loops attached, or not attached at all. But most of the flow still remains red and blue. Still retains a quasi two-dimensional, a definite circulation for each of the individual vortices. So with this, we kind of assume that the turbulence is two-dimensional with some small three-dimensional corrections. Now, the way we do the experiments is not just look at not just simply look at the nonlinear response, resonant response, but sit exactly on the resonance, and do a hysteretic measurement. Go with drive up and down, but by continuously ramping the driving pressure gradient that moves the flow around. And what we see is that, as you could guess from these peaks, this shows that at low velocities, we see a linear scaling, and at high velocity, something happens. These curves show the velocity amplitude, the position of the peak as a function of pressure gradient amplitude, going up and down. The dark one is going up, the gray one is going, the pale one is going down for several temperatures. So several values of the large scale friction. This is large friction. This is small friction. We see that a fairly complicated hysteretic behavior develops. There are even more than one stable state. More than one stable state in the turbulent regime. If you look at it more closely, the general behavior in let's say 1 micrometer and 1600 hertz oscillating flow, 1 micrometer tall, but about 1.6 millimeter in this case wide. We see that we transition from the linear laminar regime into something slightly nonlinear, then discontinuously transitions into something else, stochastically into something else again, and then there is this transition which, as we are going down, it transitions into the more dissipative state and eventually back again into the laminar. So we have a hysteretic loop, but which kind of consists of multiple loops. And this is what the critical velocities as a function of temperature look like. This second one appears only for sufficiently small large-scale friction. Now, this kind of behavior can be explained by a dynamical system. By a dynamical system where we kind of just use kind of a population dynamics, very simple predator-prey model, where a certain population of vortices, which is positive or negative, can be created either by splitting of the positive or the negative, by pair annihilation, and by external addition. And when you rewrite this into a total number of vortices and total polarization, as you get a kind of a bifurcation diagram that looks like this, where this is a vortex number and vortex polarization, so these two parameters, and this is just a kind of basins of attraction for these two fixed points. And as you vary these parameters, it depends in a complicated fashion on all three of them. But you basically get a pitchfork pitchfork bifurcation, where a 0-0 state develops into these two non-zero states. Now, in this case, the flow we were looking at was already driven mostly around flow around this sharp corner, right? We injected the energy at the larger scale, so I was talking about inverse cascade in the beginning, transferring energy from small scale into large scales. If I'm already driving the flow at the largest possible scale, probably not much of that going to happen. So for the next iteration of this experiment, we wanted to study what will happen when we change the energy injection length scale, or if we try to reduce the energy injection altogether. So we again looked at the resonator with the flow and recorder in a smaller confinement, 500 nanometer versus 1 micrometer. We tried to eliminate any sharp corner, introduce sharp corner in a more prominent way, kind of an oscillating jet around a constriction, which is about 0.5 millimeter, and the rest of the flow is about 1 millimeter, or flow through a grid. And the grid has spacing 1/10 of this channel width. So what do we hear? All right, and similar to the rotating case, we can relate this excess dissipation, which is the shaded area here, to the number of vortices in the flow, and which is how I'm going to present for the next few results. So looking again at the most basic flow, compared to here I show it for three temperatures, 1.85 K, 1.65 K, 1.45 K, where on the y-axis there's the number of vortices per millimeter squared. On the x-axis is the velocity amplitude, and the color scale is probability density function in a logarithmic color scale. Such that the darker color means higher probability of observation, because these experiments were repeated many times, and that all the observed points were collected into one histogram. So compared to the 1 micron case, we lost the strong B stability in the turbulent case. If you look at the jet case at high temperatures, we see that what we get is a development of kind of a discontinuous transition, where we have some complicated intermittent switching. It's not hysteretic, but it's discontinuous. At least it's not hysteretic in a kind of statistical sense. And if we go to the grid, we see a development of now properly hysteretic, but multiple stable states, between which the flow kind of in a complicated hysteretic fashion transitions if we go up and down. So at high temperatures, we again see maybe some sign of the discontinuous transition as in the previous case, and that splits first into about four or three turbulent branches, which then split further into many more. Kind of difficult to see here because they are less probable. But if we manually separate every branch discontinuously separated from its neighbors, we can plot a bifurcation diagram, which on the y-axis basically plots some sort of dimensional measure of each individual branches. Here it's just the number of vortices divided by velocity squared. The scaling within the branch is not velocity squared, but it's close. There are definitely some other terms there, but this is the nice property that is dimensionless. On the x-axis there is temperature. The black ones are the grid data, and the red ones are the jet data. So we see this branching. This continued branching, this branching continues below 1.45 K, but then it becomes kind of difficult to manually select what is what. But it almost looks like I don't know if you ever saw bifurcation diagram of a logistic map. At least it reminds me of that. Now, again, it would be nice if we could capture this by some sort of simple model. Turns out the model that we used previously not applicable for this. We don't really understand the reason why or how we should develop a model that works everywhere. But what seems to be working is something very simple like this. Again, we write a simple nonlinear dynamical model where the time evolution of the vortex line density is given by some large scale damping, some simple removal of vortices, and something that mimics annihilation. So at small densities, this basically scales as L squared, which would be random annihilation of pairs. But at high densities, this would turn off. And this turning off is the important part. G is just an external supply, external generation. And this fact that it turns off at high densities, it doesn't have to have this form, it just needs to turn off, is what's responsible for appearance of saddle node bifurcation, which looks like this. This dynamical system is plotted here for various values of this parameter d. So small parameter d will develop this minimum here at a maximum, and large d will be just monotonic. And as we increase g, we look for stable points, fixed points, which are plotted here for the same three curves. So as I increase g, normalize some critical g at the bottom of this minimum or equivalent number for the other curves. For this blue one, which shows the B-stability, first I go here, then I jump here, and when I historically go back, first I go up here, then I jump here. And here I have this a region of unstable fixed points, where there are two stable solutions. This, at least qualitatively, looks very similar to what we see in the jet device. Now, if you take a model like this and in a very simple way, kind of cascade it into multiple modes of distribution of the vortex line density, basically write the same equation several times, but the driving term is just related to the level of vorticity in the previous mode, and only the G0 would be the initially driven mode. We again get something that resembles the cascading multi-stability that we observe in the grid device. Now, getting the discontinuous transition of the jet device, there's something more complicated going on, and I'll go through this very quickly. So now this doesn't show the vortex line density as a function of velocity. This shows the velocity as a function of driving pressure gradient. So as we approach this discontinuity, we see kind of intermittent jumps between two stable positions, two stable values of peak velocity, where the lifetimes are changing. Okay. So, come on. Where the experiment that we did, we simply sit at every position along this oscillating or fluctuating relationship, and measure the lifetime of the more turbulent state. Average lifetime of the more turbulent state, like how the average time it takes between jumping into it and jumping out of it. And what we see is that there is some rapid increase in the lifetime as we approach the critical velocity, where the upper one becomes completely unstable, and that the scaling of the mean lifetime is quite well captured by a power law which diverges with the critical exponent 1.33 or 1.3 to 1.35. But 1.33 seems to be the best. This is close, but not quite. The critical exponent, the relevant critical exponent for two-dimensional directed percolation, which of course would not be surprising, because directed percolation is known to take role, is known to be important, or not to be the good description of statistics of transition to turbulence in shear flows, like pipe flows, coed flows, and so on. However, for us, the relevant case would be probably the planar Poisson flow, where the critical Reynolds number is about 350, which is a Reynolds number defined by the half height of the channel where you have your flow. the critical Reynolds number defined like this for us is about 10. So we are very far from seeing the turbulent bands that you would see in Taylor coed or coed flow. Right, and the last thing that I'm going to mention is that so far I talked about the influence of geometry on only lateral geometry, let's say, and I only very briefly mentioned that there is a difference between confinement, and the confinement appears to have a very strong effect, which at the moment we don't really understand. The structure bifurcations and the kind of arrangement in the space where we of observable and controlled variable depends very strongly on the level of confinement, and not in a trivial way, in such a way that it becomes more multi-stable one direction. For example, at the simplest case for the corner device, at 500 nanometers and 1.25 K, we basically see just a continuous and reversible transition. At 1.2 micrometers, we see fairly complicated hysteretic and multi-stable behavior. Now, these blue and green curves, blue are with increasing drive, green and orange are with decreasing drive. The green ones are actually, so blue would be going like that, orange would be going like that, and the green would be jumping up and then going down. And again, at 2 micron, we see very weakened hysteretic region. So with that, I should end. So it appears that there are fairly simple nonlinear dynamical systems which you can come up with for many different cases that we see with this flow. But what's lacking at the moment is a first good physical grounding in the basic equations of the fluid dynamics, and something that captures a broader class of problems. My second conclusion is that the quasi-2D turbulence can support more than one stable state, and this flow appears to transition between these states via a saddle node bifurcations. And the transitions which feature the intermittent switching between two states have a power law divergence of their lifetimes, which is close to what would be expected for two-dimensional direct percolation. All right, that's it from me. Thank you.
About your second point here in the conclusion, so did I understood properly that the different entrants that you define, that you used in your experiments, reach so many different final states? And can you explain qualitatively why the grid, for instance, seems to be the one with the most...
So my kind of intuitive explanation for this is that for this combination of frequency and confinement, this is basically the correct equation that describes a transition from, let's say, a non-condensed to a condensed vorticity state in the two-dimensional turbulent flow. But in this case of a jet, we already drive at very large scales. Already drive at scales which is half the system size. So we don't get much further modes excited. But when we drive at much smaller scale, when the ratio between system size between the large scales and the forcing scales is much larger, then there is more Fourier modes which can participate non-trivially in the flow, which gives us which makes it necessary to model more of these modes with the same dynamics, more or less. That's what I would say.
Oh, okay. So yeah, can you comment on how smooth you think your walls are, your confining walls? Because I mean, if you have vortex spinning on non-smooth boundary, then you might get more 3D-ness in the vortices than you assume.
In the the numerical simulations that I showed in the beginning, it already assumed as much pinning as possible. That there is no deepening mechanism in the simulation at all. There's only reconnection with the image vortex. So there is spinning in the simulations and doesn't seem to affect three-dimensionality at all. For the actual surface roughness in the experiment, it's about a nanometer surface roughness, which would mean deepening velocities, according to that one formula that Kurt Schwarz developed in the 80s, would be about, I think, 3 to 5 centimeters per second for 500 nanometer confinement. So we should be well above that when our critical velocities are about 10 centimeters per second.
Thank you.
But to be fair, there might be, since these are made out of 2 chips attached together, the geometry might be more complicated and more and have more defects near the edges. But they should be, the misalignment of the chips should be on the order of 10 micrometers on a flow which is 1 millimeter wide.
We take the speaker, all the speaker of the session. Yeah.